and that will allow me to draw the next resonance contributor. Drawing a series of resonance contributors can range from the fairly straightforward to the really pretty complicated. Let's look at drawing resonance contributors through 5 levels of difficulty. Ninja level 1 is a simple straight chain hydrocarbon. To draw this resonance contributor, the unhappiest place is the negative charge, so we'll take those electrons and we'll push them away from that carbon to form a new pi bond, breaking this pi bond and depositing those electrons locally onto carbon 3. This isn't a video about how to draw resonance contributors, but you can watch that video. I have it linked down below. Using these arrows as a blueprint allows us to start drawing the next resonance contributor. The new unhappiest place is the carbon in the middle, so we can take these electrons and form a new pi bond on the right, breaking that pi bond, depositing those electrons locally onto carbon number 4. That will allow us to start drawing the next resonance contributor. That puts a negative charge on carbon number 5 and completes the resonance series. We can't push out to carbon number 6. Carbon number 6 already has 3 hydrogens, and we can't make 5 bonds to that carbon. Ninja level 1 also applies to carbocations as well. The unhappiest place in this molecule is the positive charge, so I can move the bond over in a bond-to-bond arrow to form the next resonance contributor with the positive charge on carbon number 4. Now the unhappiest place is carbon number 4. It lacks electrons, so we can do another bond-to-bond arrow to move the pi bond over and put the positive charge on carbon number 2, drawing the next resonance contributor. With the positive charge on carbon number 2, that ends this resonance series. Again, we can't push out to carbon number 1. It already has 3 hydrogens on it. There's no way to draw resonance contributors that involve carbon number 1. We can also know that by using the resonance halo. If you're not familiar with the resonance halo, I've got a video that I'll link to down below for a great pro tip to make sure you only draw the resonance contributors you're supposed to by using the resonance halo. Ninja level 2 deals with abbreviated functional groups, where we have a molecule that has a condensed formula embedded within the line angle structure. If you need help deciphering these condensed formulas, I have a different 5 levels video specifically related to condensed structures that I'll link to down below. What I would recommend is to immediately redraw the molecule in its full line angle structure version without any condensed formula. That way you can really see what's going on with the molecule and if that condensed formula group will end up being part of the resonance or not. Sometimes it won't be, but unless you draw it out, you won't know for sure. Now that we've drawn out the ester, we can continue with our resonance series. The unhappiest place is the negative charge, so we can bring those electrons over for a new pi bond, break the pi bond, and deposit these electrons locally onto this carbon. And that will allow us to draw the next resonance contributor in this series. With the negative charge on carbon 3, we can see that because we drew out the ester, yes, we are going to use the ester in the resonance series. We can bring the electrons up to form a pi bond and push these electrons up onto oxygen as a new lone pair. Had we left the ester in the condensed formula, we might not have seen this and might not have drawn all the additional resonance contributors. The same is true for the pH where we abbreviate a benzene ring. Had we not drawn out the benzene ring, we would have missed all of these resonance contributors and might have said that this molecule doesn't even have any additional resonance contributors. When you see a condensed formula within a line angle structure, I highly recommend drawing it out to make sure you draw all the additional resonance contributors. Ninja level 3 is resonance where there is branching inside the resonance series. There are 2 good ways to handle a situation like this and one way that I don't really care for. Let's take a look. To start off, the negative charge is our most unstable position. We can take that lone pair, drop it down to form a pi bond. That built up too much electron density around carbon 2. So we can break the 2,3 pi bond and deposit those electrons locally onto carbon number 3 to give us our first resonance contributor. Now that we're at this position, we can go one of 2 different directions with our next resonance contributor. How should we handle that? Before we figure out how to handle that, let's go ahead and draw the next one on the right side of the molecule, and then we'll come back and look at the branching. The negative charge is the unhappiest place. We'll bring those electrons down to form a pi bond, break the pi bond, and push those electrons out to the terminal carbon to draw our next resonance contributor. To draw the resonance contributor that goes down to the bottom, what I would not recommend doing is starting with this structure and drawing a second set of arrows on the same structure. Maybe if you use different color pens, you might be able to get away with that if your instructor says it's okay. But having too many of the same color arrows on the same structure gets a little bit crowded. It's hard for me as the instructor to tell what exactly is going on. So I would not recommend doing 2 sets of resonance arrows on the same structure. Instead, the simplest thing to do is to use the equivalence symbol. These 3 lines, typically drawn horizontally, these 3 lines are a symbol that means is equivalent to, that whatever I draw here is equivalent to this original structure. We use it in math sometimes, physics sometimes. Here we're using it in chemistry. I'm going to redraw this exact structure right underneath to show that these 2 molecules are equivalent. It's not a new resonance contributor. I'm just redrawing the same molecule in a different way. By redrawing a clean version of the molecule, now I can use my curved arrows to show how I draw the branched version of the resonance without getting too cluttered or too confusing. This allows me to draw the last resonance contributor in this series. The second way to get to this same resonance contributor is to remember one underappreciated rule for resonance. All resonance contributors are related. You should be able to get from any one resonance contributor to any other resonance contributor with a single set of arrows. We traditionally draw these resonance series in a progression, and you probably should so you don't accidentally skip any, but technically you could start here and draw arrows to get you all the way back to here. One set of arrows would allow you to get all the way back to the beginning. With that in mind, the other way to get to the branching resonance contributor is to start from the position that you're at and just draw a couple of curved arrows that will eventually draw the same resonance contributor just from the different starting position. Either of these techniques will work. Redrawing the original structure and continuing on from there, or drawing several curved arrows to go from the last position down to the branching position. Either way should be fine. I would recommend not drawing too many arrows on the same structure though. If you want to spot check yourself, see how you're doing with these levels of difficulty, go ahead and pause the video, see if you can draw the rest of the resonance contributors for this molecule. Did you get 3 additional resonance contributors, 4 including the original structure? Let's take a look. The positively charged carbon is the unhappiest place, so I can take the adjacent pi bond and do a bond-to-bond arrow to draw the next resonance contributor. From here, we have some branching in the resonance. I'm going to start with the oxygen lone pair. You could have done something different, but I'm going to take the oxygen lone pair and drop it down to form a new pi bond, and that will allow me to draw the next resonance contributor. From here, I can either redraw this resonance structure to draw the next resonance contributor, or start from here and draw several curved arrows to get to the next one. I'm going to continue on with this series. I'm going to take this pi bond on the right side, bring it over, push the electrons onto oxygen to draw the next resonance contributor. That pushes the positive charge out to the right side of the molecule, and that's actually it for this resonance sequence. Did you notice there's no actual way to involve the nitrogen in this resonance series? We skipped over that nitrogen carbon when we drew this last resonance contributor. The only way we could use the nitrogen is if we had the positive charge on that nitrogen carbon, but we don't have that in this series. The nitrogen turns out to be a spectator in this resonance series and not part of our branching resonance chain. Ninja level 4 involves resonance contributors with triple bonds. And yes, there is a triple bond in this molecule. Can you find it? This is another example of a condensed structure being hidden inside a line angle structure. When we draw it out, we see that the nitrile has a triple bond and will be important in this resonance sequence. Before we get to the triple bond, this is a regular straight chain resonance sequence. We'll start with a negative charge, make a pi bond, break the pi bond, put the negative charge on carbon number 3. With the negative charge on carbon 3, we can drop this lone pair of electrons down to form a pi bond, put electrons on carbon number 5. And with the negative charge here on carbon 5, we can now involve the triple bond. Don't get too worked up over the triple bond. It still has a pi bond, so in many respects, it's still going to react very similar as if it were an alkene. It's just going to look a little bit different when we're done. The arrows are going to be the same. We'll take the negative charge and form a pi bond, break the triple bond pi bond, and deposit those electrons locally onto nitrogen to draw the last resonance contributor for this series. To draw this right side, we can use the arrows as a blueprint. This arrow says I'm forming a new pi bond between carbon 5 and carbon 6. This arrow says I'm breaking the pi bond onto nitrogen, but there's still a pi bond left over. So there's still an alkene double bond between carbon and nitrogen, and now there are 2 lone pairs negative charge on nitrogen. This is how we would draw the resonance series with the triple bond, and this closes out this resonance contributor series. So even though the presence of the triple bond makes the structure look a little bit funny, in practice it's really the same set of arrows and the same process as if it were any other pi bond. This structure is actually a pretty difficult Ninja Level 4 question. It incorporates most of the other Ninja levels within this structure. Go ahead, pause the video, see if you can work through the resonance series for this molecule. It has the triple bond in it, it has a condensed formula within the structure, and we can go one of 2 different directions for our first resonance contributor. Let's see how we can do this. We can go either direction to begin with. I'm going to start by going to the right and moving the electrons onto oxygen to draw my next resonance contributor. This time I'm going to choose to redraw the equivalent structure so I can draw the next resonance series. I'm going to start with the lone pair, move the electrons to the left this time to form a new pi bond, break the triple bond, and deposit those electrons locally onto the carbon on the left. That's going to form a cumulated double bond between 2 and 3 and 3 and 4. With series like this, I would highly recommend numbering your carbons. It's very easy to accidentally drop or add a carbon in this series. From here, we can continue moving the electrons to the left. We can take this lone pair and make a new pi bond between 1 and 2 and push those electrons up onto oxygen to draw the last resonance contributor in this series. That completes this pretty difficult resonance series and makes a pretty complicated looking molecule. When you get these cumulated double bonds, I would highly recommend drawing the carbon atom explicitly so we know where each carbon atom is in the chain. How did you do? Did you get this resonance series as well? Ninja Level 5 is a resonance series involving a radical. We don't talk about radical resonance very often in this course. You may not see radical resonance at all, but when you do, you'll be happy to know how it works. In principle, it's the same concept. We're going to be moving the radical electron throughout the chain. But because it's only a single unpaired electron, the arrows that we use to get between resonance contributors is going to be slightly different. To move around a single electron in resonance, we use the single barbed fishhook arrow. The fishhook arrow shows the movement of 1 electron instead of the normal 2. So to move this radical over, I want to make a pi bond between carbons 1 and 2. I need 2 electrons to make that pi bond. I can get one of those electrons from the radical. I'm going to use a fishhook arrow to show the radical forming half of that pi bond. I still need 1 more electron to complete the pi bond. I'm going to get that from the pi bond on the adjacent bond. I'm going to break that pi bond and use one of those electrons to form the new pi bond. but I need to account for the movement of both electrons. I'm going to take the other electron out of that pi bond and deposit it locally onto carbon number 3. I'm going to use 3 Fishhook arrows to show the new pi bond and the new radical on carbon number 3. That will allow me to draw the next resonance contributor in this series. To continue with the resonance sequence, I'm going to again take my radical. I'm going to form a new pi bond between carbons 3 and 4. I need 2 electrons for that pi bond. I can get one of those electrons from the radical and one of those electrons from the adjacent pi bond. The 2 Fishhook arrows meeting together will form the new pi bond. That breaks the pi bond on the right, and I can use that last remaining electron in the old pi bond to put it onto carbon number 5 in our last resonance structure in this sequence. Radical resonance isn't different, it's just different. We just use slightly different arrows to achieve essentially the same outcome. Whew, that was intense. I hope you enjoyed our journey through drawing resonance contributors in 5 levels of difficulty.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.